All right. Um, Two things. The review test is up there. It is a homework assignment. It says chapter 5 through 7 review test. So you can search for that, find it. I also moved all the homework assignments to be due on the 26th just to alleviate stress levels. Yeah.
Is the test due the Thursday we get back?
The test is the Thursday we get back. Yeah. Yeah. So, practice. You have questions, ask. I'll be here all next week anyway. So, all right. So we're going to do chapter 7 today. Remember, chapter 6 focused on discrete variables. Chapter 7 is going to start to look at continuous variables. All right. So first thing, imagine that a friend of yours is always late. We're going to X represent the time you're supposed to meet your friend until they show up. So remember, time is continuous. So every number between them is countable or is available. So he could show up to 30 minutes late. So when we're looking at this, unlike the probabilities that we were doing before, all probabilities are equal. We don't know, like, it could be a minute late, it could be 30 minutes late. We're not sure. So when we set up this is a uniform distribution graph, and it's basically a rectangle. And the height is the probability divided by however many minutes or what X was. So in this case, it could have been from 0 to 30. So my height's got to be 1/30. Why? What does the entire probability have to add up to? 1. So if I have my X is 30, the only thing I can multiply it by to get 1 is 1/30. So that's why my height has to be 1. So the area of this rectangle, in essence, has to be 1. Once we have that set up, we can use it to find out different pieces of it. So what's the probability that they'll show up between 10 and 20 minutes late? Well, we can just do the 20 minus the 10 and multiply that by 1/30. So the probability that they're going to show up between 10 and 20 minutes late is 1/3, or 0.333, so 33.3%. This one's doing it backwards. So it's saying there's a 20% probability that your friend will arrive in the next X minutes. So in essence, we're looking for that value right there. So if I know it's a 20% chance, that's 0.2, and that equals 1/30 times X. So now think back to our algebra class. How do we get rid of multiplication? We divide. However, in this case, we already have a fraction, right? So what's an easier way to get rid of a fraction? Multiply. So we're just going to multiply both sides by 30. So, and it's being 6. So between now and 6 minutes, my friend has a 20% chance of arriving. This method works when all the probabilities are equal, when we don't have a general trend going that we can actually make a nice little graph for. In more normal situations, though, we're going to have a curve. So these are what's known as a normal curve. It's normally distributed. We also call it a bell curve. Okay, because it looks like a bell. So they don't always have to be perfect. So like if you look here, the line, one line's a little taller than the other one. That's okay. It's allowed to be a little imperfect. The general trend of it is a normal curve. And we're going to talk about, before the end of class, how we actually determine normality. When we're looking at the normal curve, you don't really need to care about what the inflection points are. The big piece that you need to remember is, and we talked about this briefly in chapter 3. Remember the bell curve, the middle of the graph is my mean. So that's the middle of the graph. And then my standard deviation is the spread. So one standard deviation up and one standard deviation down. Or we have 2 standard deviations and 3 standard deviations. What was one standard deviation up and down? What was the percentage for that? There was a rule. It had three probabilities or 3 percentages. That was the third one. All right, it's a couple slides. We'll go back to that in a second. But it was 68, 95, and then 99.7. That was that empirical rule that we talked about in chapter 3. It's coming back. So 68 is within 1. That means there's 34 on either side of this. 95 is within 2. We can split that in half. So 47 and a half, 47 and a half. And then 3 standard deviations was 99.7. That's pretty much most of the data. Depending on how the standard deviation is, the smaller the standard deviation, the taller the graph, the more compact the graph is. The bigger the standard deviation, the more spread it is. Now, when we're looking at a normal curve, the normal curve starts at 0 is in the middle. However, my data might not always be at 0. Okay? So the middle is always going to be whatever your mean is. So we can shift that. Like the one over here, my mean is 3 instead of 0. So it just shifts it over a little bit. However, the percentages and those things are still exactly the same. Few things about your normal curve. It's symmetric. Left side and right side have to be exactly the same. Mean, mode, and median are all actually at the exact same point on a normal curve. So the mode tells you the one that appears most often. If the middle is the highest number, then therefore that's one that appears most often. If it's symmetric, that means my median's right in the middle because both sides are the exact same set amount of data. And mean is also in the middle because the data both sides would be equal in that situation. So because they're all exactly the same, we just use mean as the actual value for that. The area under the curve is 1. Even though it never actually hits the 0 or the end, it keeps going on forever. The area under the complete curve is 1. The area under the curve to the right is a half, and the area under the curve to the left is a half, because they would have to be equal in that respect. As I said, as the values increase, x goes up, are further and further away from the mean. It never actually hits the horizontal axis. It gets really, really close, right? But it never actually reaches the horizontal axis, which means technically any of those values could happen. The empirical rules, what we were talking about a few minutes ago, 68%, 95% is 2 standard deviations, and 99.7 is 3 standard deviations. You're never going to need to know the actual, the specific wording of this, but you're going to need to know how to use it. That's why I'm kind of going through this quick to get to the ones we're actually going to be using them. It'll make a lot more sense once we start doing it. All right. Here's a relative frequency distribution. So here's all our data. And it kind of looks symmetric, right? It's not perfect, but it's close. They're telling me that the mean is 38.72 with a standard deviation of 3.17. Okay. When we get enough data, like this situation like here, you're pretty much going to be assumed that it's going to be a normal curve. So if we graph this all, here is the curve. This is a what type of graph? What other type of graph? What graph is it though? It's symmetric, but it's also starts with an H. It's a histogram. Okay. So it's a histogram that makes the bell curve. Yes. So our mean was, what did they say, 38.72? And that's like right in the middle of there with the 38. Sounds about right. And then our spread was, or our standard deviation was 3.17. So it's basically got that. So it wants us to compare the area of the rectangle for the heights between 40 and 49 to the area under the curve. So what was the relative frequency between 40 and 49? 40 point, was it 40 and 40.9? So if we look here, between 40 and 40.9 was 0.11. Okay. If we look at this as a bell curve, do I have it or do I have to do it? Of course I didn't do it. Why would I have done it? It is this one. All right, so here is my, actually, you know what? I'm just going to do it on the site. Hold on a second. So I can zoom in a little bit better. All right, so here's my bell curve, and we're looking, my mean was 38.72. And standard deviation was 3.17. And we were looking between 40 and 40.9. So between 40 and 40.9, and actually, because it's not equal to, it's actually literally between them. You go a little above, a little below. So I got 0.1189. Let's see what they got. And what was the actual percentage in the problem? 0.11. So it's pretty close. Is it going to be exact every time? No. Because if we look at the curve, it's not always going to be like exactly that box because it's a rectangle and we're turning it into a curve. So it's estimating it. But it's going to be pretty close to what was actually there. So we talked about before experimental and theoretical. This graph right here was built on an experiment. We have the actual data to graph it. Where this curve is more of the experimental. We have the data, and we're going to be able to estimate a lot of other values from that. Does that make sense? The difference between the two? right. The serum total cholesterol for males between 2029 is approximately normally distributed with a mean of 180. So change my mean to 180. And my standard deviation to 36.2. Actually, you know what? For this one, it's better to use the other calculator. Nope, not going to help me. All right, so we have our bell curve. It'll look like this. If I looked between the 143.8 and 216.2, that's one standard deviation, and it's right approximately the 68%.
What number calculator is that again?
This one is 24. Yeah, the two calculators we're going to use today is 24 and 26. If we're looking for a total cholesterol greater than 200, go greater than 200. Approximately 29%. You can start to see where you're shading. So if we're looking at greater than, we're looking at over here. If we're looking at less than, we're looking at this side. What do you notice about, so I got 29.03, and the other one's going to be 70.97. What should those two add up to? Should add up to 1, right? Those are complements of each other. So depending on how you're doing it, sometimes it's going to be easier to find one direction than the other direction. All right. Now let's actually do some real problems. We talked about z-score before, briefly, and then I said we'll cover it again later. Z-score tells us the amount of standard deviations that are between that value and the mean. Okay, so it basically standardizes it, so no matter where the value is, this is going to tell me how many standard deviations I am away. So to do this, you need to know which value we're looking at, the mean, and the standard deviation. This is not a formula I have a calculator for, so make sure you have that because we're going to use it a lot. And remember, x is the number, that's the mean, that's the standard deviation. when you're looking at the normal curve, in the middle, my z will always be 0. To the left, I will always have negative z's. To the right, I will always have positive z's. So negatives to the left, positives to the right. So IQ scores has a mean of 100 and a standard deviation of 15. So an individual whose IQ score is 120 is 1.33 standard deviations above the mean. Let's see something. I'm trying to think of which calculator is going to be used for this. I just have a z-score calculator. But that's not going to help me for this one. All right. So a pediatrician attains the heights of 3 of her children. The heights are normally distributed. We did this 38. So my mean is a 38.72. My standard deviation is 3.17. What proportion of 3-year-old females have a height less than 35 inches? So while you don't necessarily need to figure out your z-score for this because you use a calculator, you will most likely need it for your homework. So I want 35 inches minus the 38.72 over the 3.17. So that's all you're doing for that. So 35 minus 38.72. What sign should this z-score be? Looking at the data, it should be negative, right? Because the value I'm looking for is to the left of my mean. And in this case, my z-score is negative 1.17. So now we want to know what the percentage of that is. So 38.72, 3.17. And we're looking for less than 35. And if you notice right here, it gives you the probability and the z-score. So my z-score was negative 1.1735, and we got the negative 1.17, which is fine. We rounded. And the probability is going to be 0.1203. Does the number make sense? Because, so the biggest thing that you're going to have to do with this is make sure that your number that you get makes sense for the problem. Okay? So we know that this is more than one standard deviation away, correct? So if we're looking back at my wonderful little bell curve that I had all those numbers under, we're liking over here, this area, because we're more than one standard deviation away. So yeah, that kind of makes sense. That's 13, another 2.5. So yeah, about a 12 kind of makes sense because we're going to be somewhere in this area over here. So if you got a number that was like 30%, you should be able to look at it and go, something doesn't seem right here. Go back and check your calculations. You might have made a mistake somewhere. Okay. So that's really the biggest piece to a lot of this, is it's less about looking and making sure that like you understand all the details behind it. But it's understanding that when you get an answer, it's like, okay, does that answer make sense for the question? So in this case, I'm more than one standard deviation below, so the 12% kind of makes sense for that. If I was closer to 0, I'd be closer to the 50%. The farther away I get from 0, the smaller those numbers are going to end up being. All right. Find the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. I have to see something before we do this problem. Because I know they don't use a table. I want to know exactly what answer they get. I just want to make sure I get an answer that's the same as theirs. All right. So we're going to go back to my wonderful table. We're going to go between 35 and 40. 40? 0.5365. Perfect. Then I don't have to worry about it. Does that make sense? That it's over 50%? Well, yeah, because if we're looking at this graph here, I know that, well, first of all, we're over the mean. So this was only like 12%. So that right there has got to be 38% because that's got to add up to 50. So yeah, over 50 kind of makes sense for this problem. Okay. The funny thing is that we used to do this all with a table. You'd find the z-score, you'd look in the table to try to find the values, and we'd have to subtract them. I was told not to use the tables, and I was told to use the technology. So this actually makes your life easier. When you're looking at there's 3 different types of problems or things that you'll see. When you're looking to the left, you're going to shade to the left. When you're looking to the right, you shade to the right. When you're looking between, we're shading in the middle of it. So depending on which direction you're going, I know some of the questions ask you to do the shading to see which one you're shading first. So do that, find your z-scores, and then you can use technology to find your final answer. All right, there is a couple things. And I'm not sure, let's see. All right, so see how this thing gets 1? Technically, you'll never get 1. Okay? You can never get 1. However, when you get so high, the calculator is going to round. All right? Every calculator is going to round. So if you get an answer as one, you do not put 1. You put 0.99999. You just put a bunch of 9s. That's as close as you can get. The opposite direction is also true. If you get a probability of 0, don't put 0. Put 0.00001. Okay? It's close, but it's not exact. Okay? So when you're writing it, don't just put 1 and 0. They're going to be slightly off of those. All right. What if I wanted to find the height of a 3-year-old that's in the 20th percentile? We're going backwards for this. Okay. So if we look at the calculator, I have find x value. And we're going to want the 20th percentile, so change that to 20th. Now, it's going to ask left or right tail. Okay. So that's the 20th percentiles right there. This would be there's 20% over here. That'd be the 80th percentile. So when they're asking percentile, it's always from the left over. So if I wanted the 75th percentile, that's from the left over to there. Okay. So anytime they're asking percentiles, it's always from the left over to that value. So it'll always be a left-tailed experiment. So the height of a child in the at 3 years old, or a female child at 3 years old, for the 20th percentile would be 36 inches tall. We took the PSATs at some point. Scores earned on the mathematics portion of the SATs was approximately normally distributed with a mean of 516 and a standard deviation of 116. So we go back to here, 516 and 116. What scores separate the middle 90% of the test takers? So, this one we have to do a little calculations for, because I don't have the middle 90%. So what am I going to have to find? If I want the middle 90%, so I want something that looks like not quite that, but all right. I want 90% in the middle here. So how are we going to do the calculations for this? Yes, we could sit here and keep playing with the numbers so we can get 90%. But how do I know that's exactly the right split? I don't. So what percentage is going to be down here? Why 5? Right. So if I want 90% in the middle, there's 10% left over, right? So I'd want 5% on either side of it. Okay. So if we go to this one and I do 0.5, that's now going to give me the lower 5%. So that's 325. And if I click right tail, that now gives me the 5% on the other side. So that goes up to 707. And if I took 5% from both sides, I have exactly 90% left in the middle. So it'd be 325 to the 707th. Okay. All right. So you will see the symbol Z with a little a underneath it. That's alpha. And it's telling you the area to the right of the curve. So Z.25 would mean that percentage right there is 0.25% in that little area right there. Which would mean how much would be on the other side? 0.75 over there.
Oh, I think about that.
Yeah. I got what you were meaning by this point. All right, so it's 0.75 on the other side. So if I want to find the value of Z with a 0.1, now I can use this calculator to do this. If I do the 10 there, the right tail, the answer they want is the Z-score. Okay. They don't want, so it actually does not matter what your mean and standard deviation is for this. I don't even care what those are. All I really want is the Z-score down there. So that 0.1 or 10 is 1.2816. That makes sense? All right. Let's do the uh, 63.5 inches. And 2.5. I'm going to make you work right now. So 69.2 and 3 inches. Find out what percentile you're in. So find your percentile of your height. If you don't know your height exactly, it's fine. You can estimate it. You're finding your percentile for how tall you are. So all you're going to use is this, find probability, put in the mean and the standard deviation for what you are, and then you're going to use less than and put in your height. So I'm in the 72nd percentile for my height.
So I got 30.34, so I subtract that from 1 to get the percentile when I did like out on the calculator.
Oh, you did the other direction? Yeah.
Yeah.
Yeah. Which calculator did you use?
I just my phone.
Oh, okay.
I'm assuming I probably would have got the correct answer.
So wait, what did you get on your phone?
I got 0.34.
How did you get to 0.34?
I'm 72.
Oh, you were so you'd be in the 82nd percentile.
You're supposed to subtract 72, or if I was,
That gives you your z-score. That doesn't give you your percentile. So if you did 72 minus 69.2 divided by 3, you'd gotten 0.9333.
Oh no, I got 0.34. That's weird.
My guess is you subtract, when you typed it in, you might have subtracted wrong. So if you find your z-score, that's one thing. That'll get you your z-score. You then need somehow to be able to convert it to a percentile.
Gotcha. Yeah, no, I just did it wrong.
Yeah. So that's where a calculator comes in. StatCrunch can come in. If you actually have the book or look, there's tables in the back of the book that'll help you with it too. I'll actually show you the table. The tables are actually kind of cool. Z-score table. And I like, we can use Arizona. So this is what the z-score table is. So if I looked up mine, which was 0.6 for my z-score. So if I look up 0.6, 0, there's the probability right there. So the table gives it to you. The problem is the tables only have specific numbers. So, like for your example, you were at 72, I have 0.9333. The threes keep going. I could find on the table the 0.93, and I can get close, 82.381, but that's not exact. So the tables were designed before we had computers and calculators and stuff like that to be able to easily find those percentages. They did all the calculations were already done. You could just look at the table, get your answer. So, all right. All this only works if it's a normal graph. If it's not a normal curve, we can't do that. But if I can show that it's a normal curve, then all the stuff we just did works. So how do we determine normality? All right, so here's what we're going to do. I've kind of made this easy. So I cut it up. That's right. So the calculator you're going to use is 26. It is the normality assessment tool. So what this tool does is you're going to type your numbers in here, and it's going to graph them. So like, does that kind of look like a line? Look pretty linear? That's what you want. The data should be pretty linear when you look at a graph like this. These aren't like, because I'm only graphing one number. So you're not actually graphing the points. You're actually graphing the value as compared to what you'd expect the z-score to be. So there's doing a whole bunch of calculations behind it. But the goal is to get it to come out to be some kind of a straight line there. If I was to add in, say, 99, now you can see how that's straight, but that point right there doesn't seem to kind of make a nice thing because it's way out there. But if I just added 51, it's not perfectly curved. I mean, it's not a perfect straight line, but it's close enough that we can still consider it normal. So for this problem, I'm just going to take a picture of my phone so I don't have to keep flipping back and forth. We would type in 31.35, 32.06, 31.91. Did I miss a decimal point or something? Nope, I did. Okay. All right, so here is my points. I have 6 points. You're going to get two numbers. You are going to get your correlation, your R value, which some of the questions in the homework ask you for that, and your critical value. As long as your correlation is bigger than your critical value, you're good. It's normal. The data is likely normal, and we can use the normal curve and those calculations for it. If it's not, if it's the other direction around, it wouldn't be normal. I do want to show you one of the homework problems. Come on. Give me code. All right, so here is our data for this one. When you copy and paste it, you can copy and paste it right into my calculator. However, what it does is it doesn't put the commas after it. So you have to go back up and put the commas after it. So now, that doesn't look like a very nice line of data points. But its correlation as compared to its critical value is still higher. But notice, they're a lot closer than the last one I did. Okay? So even though it's not a nice straight line, the correlation's still bigger than my critical value, so that would be normal. When we type this in, we would say yes. And the first box says the correlation between it, that is your R score. That's that correlation. So it's 96414. And then the critical value is the other one, 0.941. Why? Give me the answer. I rounded it to too many places. Oh, it does say rounded 3 places. Okay. Note to self. Make sure to read the question and round to the correct decimal places. All right, so that's all you have to do for that one. I think there was one. Carolyn, which one was it that had the two set? Nope. That's chocolate chips. Oh, this one. When you copy this one, you actually, I wouldn't copy this one. You just want the observed value. That's all you actually want. It'll calculate all the rest of this stuff out for you automatically. So, but if you hit copy, it has all the data there, and you really don't want it all. You really just want that observed data. So it's probably easier to just type that one in than to copy and paste that one in. Ooh, the chocolate chip cookie data. So all you're going to do, copy, paste it in. Put a bunch of commas after them. I can. You don't want to have to put all the commas in? The problem is I have to actually let it do both, because if you put it in a list, like, I will add that for you. So here's another one. What do you notice about the critical value? So this one is less, yes, so this one's normal. But the more points I put, now it's never going to go up again, or is it? I think that's actually the highest it'll go. Yeah, there we go. Because that's about the highest it'll go. The more data points you have, the bigger your critical value is. Okay? So as you get more and more points, your critical value goes up. Okay? Here's a good example of one that is not normal. Just throwing some numbers in there. So my critical value is 0.880 because I only have 5 numbers. But my correlation is 0.8617, so therefore it's not normal data. All right. StatCrunch literally gives you the exact same thing this does. Because I fixed it today to make sure that it did exactly this. So, any questions? Your test is a week from Thursday. So we'll do the review on Tuesday. Your test will be Thursday. Review's up there. Remember what I said, I would do it 3 times. I try it once, go back and go over it, go back and do it and write your index card, and then do it one more time. Yeah.
Is this practice test as similar
It is a home, yeah, it's going to be,
as the other one was?
Yep.
Okay.
yep. And I've set it as a homework assignment, so therefore you can skip around and everything else is like your homework, unlike the last one.
Yeah, because this one tells you, I noticed this one tells you right or wrong.
Yes.
Before you do that.
Correct.
So-
Yeah. That was a couple of little things on the what I did as a quiz didn't do it. So, all right. I will see you after spring break. And
Next week is spring break.
Yeah.
All right.
enjoy your trips to Florida, right? The 26th. Yeah. Yeah, I changed the due date on it, so you're fine.
Awesome. Thank you.
You're welcome.